Okay, we just learned the alternating series test, and we did one example that was in fact convergent. And now we're going to do another one and see if it's convergent or divergent. So first I'm going to look at, is this increasing or decreasing? So it's kind of hard for me to tell. It's definitely alternating series because we got that -1 to the n. And then the question is it going to be increasing or decreasing? It's hard for me to tell what's going on with this, so I'm just going to plug in a few numbers. When I plug in n equals 1, I get 3 times 1 is 3 minus 1 is 2 on top. 2 times 1 is 2 plus 1 is 3 on the bottom. And then that's going to be negative because -1 to the 1 is -2/3. So this is my sequence b sub n. Now I plug in n equals 2 and I get 5 on top, and on the bottom I get another 5. And now that's going to be positive. My next one's going to be a negative. Actually, you know what? I can just ignore the negative and positive because all I really care about when I'm looking, now that I know that it's alternating, I'm really just looking at the this part of the sequence. So when I plug in n equals 3, I'm getting 8 on top and 7 on bottom. This doesn't look like it's increasing at all. Or sorry, it doesn't look like it's decreasing at all because I started out less than 1 and now I'm greater than 1. And each time I add like a larger n, I'm going to be multiplying on top by 3 and on bottom by 2. So that's going to be making my expression larger. So this is increasing. So it fails part 1. Now, here's the trick. Does this mean that the series is divergent? No. So the alternating series test can't be used because the alternating series test says if you have these two conditions, then you're convergent, but it doesn't say what happens if you don't have one of those conditions. So instead, what we're going to do here is let's look at the limit as n goes to infinity. This would have been my part 2 anyways. 3 to the n minus 1 over 2 to the n plus 1. Well, basically, this -1 and +1, when you have large n, those aren't really going to do anything. So this is going to be more or less like the limit as n goes to infinity of 3n over 2n. The n's are going to cancel. That equals 3/2. In particular, that's not equal to 0. So if your terms of your sequence are not going to 0, then your series diverges by the test for divergence. So the series diverges by the test for divergence. All right. So I've seen one that converges, one that diverges. Now try exercise 5 and see what happens. Ready, set, go. Pause the video and try it, and then, come back and see what I did. Okay, here we go. Once again, definitely alternating because we got that -1 at the end. So we're just looking at our sequence b sub n here. That's 2 to the n plus 1 over 3n minus 1. If I start plugging in some terms, plug in n equals 1, and that'll be a 3 over 2. Plug in n equals 2, and I get 5 over 5. Plug in n equals 3, and I get 7 on top and 8 on the bottom. So yeah, this is decreasing. At least it looks like it's decreasing. And in particular, what I can say about this is it's like I'm multiplying by 2/3 for each term. Because I've got the 2n on top and the 3n on bottom, my denominator is going to be increasing by 3 and my numerator is going to be increasing by 2. So that's going to end up making it decrease over time. So Part 1, it is in fact decreasing. Ding! Part 2, what is the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n minus 1? You can look at this just like we did above and say, oh, it's going to be like 2/3 or 2n over 3n. If you wanted to be completely precise, you would multiply top and bottom by 1 over n. And you'd end up getting the limit as n goes to infinity of 2 plus 1 over n divided by 3 minus 1 over n. Both of these go to 0, of course, when you take that limit, and you just get 2/3. So this diverges. It fails the AST because this is 2/3, it's not equal to 0. And it diverges by the test for divergence. Because the test for divergence says if your sequence is not going to 0, then you're definitely diverging. And the big remark here is you cannot say something diverges by the alternating series test. It only proves convergent. Typically, if you're failing the alternating series test, it's common that you are going to also diverge by the test for divergence. So that's often the one we used, but not all the time. All right, let's talk about absolute convergence. We say that a series is absolutely convergent if the sum to infinity of a sub n, the absolute value of it, is convergent. So this is a stronger statement than just regular convergence, right? Because you might have some negative terms in a series that are sort of counteracting some of your positive terms that make something converge. But if you're taking the absolute value, that means you're making everything positive. Every single term that you're adding in that sequence is positive. So absolute convergence is stronger than just regular convergence. And then definition 7, if a series converges but is not absolutely convergent, we say that the series is conditionally convergent. So you might see that term some other places. So let's do some examples. I've got the series sine n over 8 to the n. If I look at this same series and I take the absolute value of the whole thing, I don't know what that's exactly going to equal, but it's definitely going to be less than or equal to 1 over 8 to the n, because the absolute value of 8 to the n is just 8 to the n, and sine of n is always less than or equal to 1. And this thing converges, and how do we know it converges? It's geometric with r equals to 1 over 8. And this implies that the series sine of n over 8 to the n is absolutely convergent. All right, how about this one right here? If I take the absolute value, the sum, n equals 1, of the absolute value of negative 1 to the n minus 1 of 1 over n, well, what that really does effectively is it just makes this thing go away, because the absolute value of negative 1 to a power is just going to be 1. So this is just the sum, n equals 1 of 1 over n, which diverges, because it's a harmonic series. So the sum, negative 1 to the n minus 1, 1 over n, that actually converges. We proved that up above. That was, where was that one? That was this one, example 3. So we know that one does in fact converge but it is not absolutely convergent. In particular, we would say it is conditionally convergent. And theorem 3.1 says if a series converges absolutely, then it is convergent. And this has to do with the fact that basically if you are, if you're adding up a whole bunch of, well, if you're adding some stuff together and you've got positive and negative terms, if you made all those negative terms positive and you still converge, then those negative terms would only be canceling out some of those things you would have converged to. And one way, this doesn't actually prove completely that it is convergent, but one way to think about it is if I know that the series of when I add up, I know it's absolutely convergent, so when I add up the absolute values, I get to some constant c. Well, that's definitely going to be larger than what I get if I'm just adding up the terms. And it's definitely going to be, the actual series is going to be greater than what I get if I took the negative of the absolute values one, and this is going to negative c. So this means that my series that converges absolutely, it's definitely going to be bounded. I would need to prove something more. I would need to show that it's monotone in order to say for certain that it converges. But that at least should give you a justification to believe why it is in fact convergent. All right, we're going to end this last video by stating the ratio test. And then once we've done that, we'll give you some awesome examples about why the ratio test works. I think we'll do that. Oh yeah, and then we'll have a whole bunch of fun examples. Okay, so the ratio test, let's write it out. So if you take a series, sum to infinity n equals 1 of a sub n, and if you take the next term in the series and divide it by the previous term, if that happens to be less than 1, then the series is absolutely convergent. And I'm taking, the absolute value of that. If I take that absolute value and it happens to be greater than 1, or infinity, infinity also being greater than 1, then the series a sub n diverges. And if you take that limit and it happens to equal 1, then we don't know. The ratio test in that case is inconclusive, and you have to use inconclusive. You have to use some other test in order to figure it out. So I have to try some other test for convergence. And this might look sort of strange, but the idea of the ratio test is that you're comparing one term of the series, one term really of the sequence to the next one. And if you can see that that's getting smaller and smaller in a certain way, then it's going to converge. And this II here, if that ratio is greater than 1, it means that your next term in the sequence is getting bigger and bigger. And if you're getting bigger and bigger, then you're not going to be converging. And if it happens to equal 1, lots of weird things can happen. All right, we'll stop there.